first announcement, hopefully you guys enjoyed yesterday going out and helping people in the community, doing community service there with the Project Impact. Tonight is the Harvey's Harvest picnic out at Harvey Meyer's house. And there's limited parking, so don't drive unless you have to. They're providing transportation. But I put the address here. It's at 6 p.m. If it's rainy-ish, then they're just going to do it in the atrium here by the library. So that's the backup plan. So, and I actually read Pastor Rich's email with the instructions. Another thing, I got an email from one of our students at Southwestern, and the Southwestern volleyball team will be here to play volleyball against us on Saturday night. Is there anyone in here that's on the volleyball team? No. Pretty sure Colton's not. So we do have two of our students that are... Oh, is Megan here? Okay, I didn't have you marked as here or not here. There are two of the students there in the class that are in the Southwestern team, so they're going to be here, so you can go see two of your classmates in person, live. Okay, so those are my announcements for the day. Let's go back to the last slide we talked about last class period, and that last slide was talking about Newton's 3 laws. Remember, I wanted to make sure I covered that slide real quickly because you had one homework question that's on it. Now, I know that homework's not due until, 7:35 tonight, but I wanted to make sure that you at least had a chance to work on it after class and not be like, well, I'll have to wait. Speaking of homework, remember next Monday will be a review lecture, and then Tuesday during lab time will be the exam. So there's no pre-lab quiz for Tuesday. And the homework assignments are tied to the lectures. They come in the next lecture after. And so our next actual lecture, I'm presenting new materials on Wednesday. So there's a homework due tonight, and then the next one will be due next Wednesday. So they won't be due on Monday, the night before the exam. So you have a little more time you would have devoted to physics study to preparing for the test. Okay, so looking at those 3 laws of motion again that Isaac Newton developed. The first one, the law of inertia, is a statement about natural motion, that things naturally travel in a straight line at a constant speed. Putting those together, that's called constant motion. Constant motion is identical to saying constant velocity. So the natural motion of things is to travel with a constant velocity. This is in contrast to what Aristotle believed. Aristotle believed, based on just practical example, if I take this and I slide across the table, it stops, hence the natural motion must have been to be at rest. But Newton said, no, that's not the natural motion. The natural motion is just to keep doing whatever it's doing. And something has to affect it to make it change its motion. Now, we can all look at this, and we all have plenty of understanding. What made the remote stop when I slid it across the table? Friction. So the force of friction there was something that acted on the remote to make it stop. Here's something cool I just realized. I can actually see which one of the 2 feeds they're getting in the other classroom because there's a screen on the back that shows me. So that's kind of cool. He changed so that you could see me slide the remote. Now, of course, I didn't warn him, so he may not have been in time, but good. Thanks for trying. Okay, the second law, you don't need the first law once you get to the second law because acceleration is the rate at which velocity is changing. And so the first law says acceleration is 0 if there are no forces acting on an object. The second law says if there are forces acting on the object, then the acceleration is given by this equation. So, what are you doing, Maranatha? Okay. Like seeing students disappear into the stock room. So this here, the second law is the one that tells us a lot about what's going to go on in life. So in basically all of our problems we're going to be working for the next week or two, we're going to be focusing on this second law. I put it in this form. I just wrote over the thing that shows the vector sign. I put it in this form because very often it's the acceleration we're looking for, but we also see it very often written as now, I know I mentioned this at the end of last class period. One of those has the Greek letter sigma. It's a capital sigma. The other one has the word net. Those must be equivalent, or else I would have made a mistake if they weren't equivalent. So net means add them all up together, and what's the resultant? That sigma means sum them up. So in the end, they are indeed, they mean the same thing. So you can write it either way, with a sum and then force, or with that net, saying it's the net force. Now, when you look at this, I make a really big deal that this equation is not correct. And you can put the vector signs, it's still not correct. Why is that incorrect?
It doesn't tell you the net.
Yeah, it doesn't say the net. And people make mistakes like saying, well, that mass sitting on the desk, or to take an example from people in Southwestern, that water bottle sitting there in the front corner of the desk, it's not accelerating. And so the force on it must be zero. And you say, but I know that there's a gravitational force on it. And you say, well, is that gravitational force zero? Well, the answer is no. The gravitational force is not zero. But you have the equation wrong. You have to put the sum of the forces, all of the forces acting on that water ball, or all of the forces acting on that mass, have to add up to zero if the acceleration is zero. So that's why you have to have the summation. Right? So like on the test, when you're writing your equation, if you just put F equals ma, yeah, I'm not going to give you the full credit on that because it's not right. I mean, it seems like a technicality, but it's a super important technicality. Since I know his name, hey, Manuel, nice to see you. He waved back. Okay, so that's Newton's second law, and we're going to use it a lot because it relates motion, acceleration, with the forces. We call it dynamics when we're talking about why things are moving. So that's the equation that's our key for starting dynamics. Now, later on, and I haven't looked at who it is, but there's somebody who's gone through like starting chapter 7, I think, on the concept codes questions. So they've already gotten past this. We'll learn about using work energy for dynamics. It's a second way of doing it. Honestly, work energy is easier if you can use it, but we have to understand forces carefully before we get to the work energy. So that's why we do the force method first. Okay, the third law, equal and opposite forces. For every action, it's an equal and opposite reaction. Action means force. And basically, remember last class where I used the example of punching a hole in the wall after the officials took away the fumble after Charles Woods stripped the ball from Tom Brady, who was holding it with two hands in front of his chest. The point of this being, when the NFL changed the tuck rule, former Raider executive, I can't remember his name now, but he asked the head of officiating and described that situation. Now, would that be a fumble or not? And the guys that were explaining said, no, that would have never been a fumble or an incomplete pass. It always would have been a fumble. And then he really started burning up, and everybody laughed at him because, I still feel we got cheated. Okay, so Newton's third law, for every action, there's an equal opposite reaction. When I punched that wall, it punched me back just as hard. Of course, that wall was just drywall, so it wasn't very hard. Why did the drywall break and not my hand? Because my hand it's harder, he said. It has a higher ultimate strength. The force that it can withstand before it breaks is higher. Now, back when I was in high school working at the dairy, I had you got these little narrow lanes, a cow coming toward me in the lane. The big thing they tell you in the dairy is don't let a cow go past you, because if they roll you, it will just roll you around and break bones in your pelvis, Not good. I had a girl a year ahead of me in high school who actually had that happen. And so she was laid up for a few months, And so to try to stop it, I punched that cow right in the noggin. And you know what's stronger between my knuckle and a cow's head? Yeah, the cow's head. Broke my knuckle, but didn't break anything down here. Okay, so Newton's three laws. That third one is probably the most confusing of all of them to people. I can tell you these things, but then I give you a problem. They just lost us over there at Southwestern. There.
Lost the slides.
Oh, they lost the slide. Oh, so
Yeah.
it's this that went away. There's no internet connection. How wonderful. Let's see if I can reconnect. What was that?
You can play a game by pressing the space bar.
Yeah, I don't want to play the game right now. Okay, I truly have lost internet connection on this thing. That's a bad thing, but
It looks like it's in airplane mode. If you turn off
no, it's. I actually haven't figured out what the airplane means, but it should be connected to that one. So
if you disable airplane mode, it'll connect again.
I think it's just the internet.
there's disabled. So now re-enable.
Oh, yeah, the internet's
Actually, it's saying connecting now.
Please just turn your back on.
Yeah, we're in some good business here. Connect. Now it says, yeah, I don't have them.
You can use student.
No, I can't.
Oh.
Well, we're in grand luck. I guess you'll just have to hear me for the rest of the way. I'm sorry, but I don't even have that password. I don't know why it got disconnected. Maybe it'll come back at some point. Like I said, I can't actually use it.
Can I use it for you?
No. Okay. Coming back to the lecture, and I guess you guys just have to watch me wave my hands and whatnot for the rest of the time. I can give you an example, like on that little placement test we had, where you have a car that's pushing a truck up a hill. And it asks, which force is bigger, the force of the car pushing on the truck or the force of the truck pushing on the car? The answer is they're equal. But most people, even after being told, equal and opposite forces, if A is putting force on B, B is putting force on A, they tend to still answer this the way it always felt that, yeah. Actually, do you have the camera set so they see this? Thank you. Okay. So they always answer it like, well, I know that car is going to take a lot of damage and the truck won't. And so they make that mistake of damage with force. And they have the same force, but the car's just not as strong. Okay, so free body diagrams. We're going to be working with force problems. I'm going to introduce a bunch of forces in just a moment. And when we're working with forces, we're going to draw free body diagrams. So not on the exam next week, but on the next exam after that, you're going to have tons of problems. We're going to draw a picture and show the forces acting on it. Because a free body diagram is a diagram that shows all of the forces acting on the object you're interested in. Notice it was the object you're interested in, not all of the forces entirely. So in this picture, we have a skater with two other skaters pushing her. If you look at the forces, there are only two forces that it shows in the horizontal direction acting on her. One from the push of person one, one from the push of person two. Those aren't the only forces in the horizontal direction. What are some other forces in this picture in the horizontal direction?
Force of her pushing back.
Okay, force, that's what I was hoping to hear. The force of her pushing back on the skaters those are also forces going on in this picture. But the free body diagram is looking at the object we're interested in and only the forces that are acting on it, not forces that it's putting on other things. So in this case, you show those two. Now look at this picture here. That's technically the free body diagram. That is showing the body, so that dot represents the ice skater, and then it's showing arrows for the two forces acting on her. You can draw it like that. I am happy for you to leave it like this, just showing the forces acting on the person. You don't have to have a separate picture with the dot and the arrows. I'm happy to say your free body diagram, you have a diagram, you chose the object you're interested in and drew all the forces acting on that object. Well, why do we do all this? Why do I require you to draw this? I will answer. It's a rhetorical question there. The answer is real simple. Because when you're applying Newton's second law says the sum of the forces on some object is equal to the mass of that object multiplied by the acceleration of the object. Now, it's a vector equation, which means that if you have two dimensions, such as in this picture, you'd have the sum of the forces in the horizontal direction is equal to the mass of the object times the acceleration in the horizontal direction, and the sum of the forces, well, I said horizontal and vertical because that's what it looks like on the screen. So if you have three dimensions, then you can actually make three equations from it, one for each of your coordinate directions. So here's an example that goes to the lab we did this week. We had a cart. There, now it's a cart. And that cart, we didn't identify forces on it because we weren't thinking forces. We weren't doing the experiment talking about why the cart moved per se. We were doing the experiment to just say, how does it move? So we didn't talk about the forces. But if you were to look at the forces acting on it, there are three that are shown here. The three are, well, three that we're going to talk about. I really am just showing this so we can see the free body diagram with the forces. Just for your knowledge, this one here is called the normal force. And as we'll see, I think in the next slide, normal is a direction, not common. This one here is the force of friction. And this, well, depends on if it's moving or not, if that's going to be static friction or kinetic friction. And this one here is the force of gravity. Now, this book is not the book that I would write. And one of the differences between this book and me is I make my symbols for forces so they all start with an F. That way, if it starts with an F, I know it's a force. So I don't label this W, especially because later on W is going to be the symbol for work. So I label it F with the subscript, and then the subscript tells me which of the forces it is. And I usually use a lowercase g if it's equal to mg. So I would have called this F sub g. This one here I would have called F sub, and I'll put KF just for kinetic friction, assuming that's sliding. And that one I would still call F sub n for normal force. So when you are labeling, you're free to choose what labels you want. I will be labeling forces with an F and a subscript. You could label them, like the textbook does, as long as you understand it, and when you're doing your solutions for the test, you make it clear what you're doing. It's fine whatever symbols you use for them. Okay, so our first clicker question, and thankfully the clickers are on the one that's still working. Not so much my brain, it's there. So you can start answering now. What is the ultimate reason we draw free body diagrams for force problems?
Channel 33.
Channel 33, yes. Or session ID WebPhys. Okay, give it about 10 seconds. Okay. We had our answers here. 8, 5, 7, 22, and 8. Once again, no majority. Because I have a lot I want to cover, I'm just going to take this random person and have them explain their answer. So, not having paid attention. I hope Courtney Hanna is there at Southwestern. Is Courtney there? All right, excellent. Courtney, if the person there, I'll turn on your microphone so we can hear you. Thank you. Explain which answer you chose and what your reasoning for it was.
I picked A so we don't forget force, because if you write out everything, you see all of it. That's why I figured you draw a free-body diagram just to note all the forces so you can get one.
Okay, that's a very good answer. I'm happy with that. So we don't forget a force. That's part of the reason to use a free body diagram. Now, that wasn't the only correct answer. This one here, there were other correct answers. So we can show the teacher that we know what we're doing. Well, on the test, that is kind of part of what we're looking for everything, right? That's why we give questions. The Newton's first law, not so much. We don't do it for that. It's the second law that's really important to us. And you know what? It's not the third law for one very simple reason. Not the third law because your free body diagram is only looking at the forces acting on the object you're interested in. So you're not showing the Newton's third law forces. If I'm going to make a free body diagram for this mass, I'm going to show the force of gravity pushing down on it. I'm going to show the force of my hand pushing up on it. Those are two forces acting on it. I am not going to show the force of this mass pushing down on my hand because that's acting on my hand. So I'm not showing the Newton's third law force there. Likewise, I'm not going to show the force of this mass pulling up on the earth because that's not acting on my hand. That brings up another interesting thing about the third law. Sometimes people get confused about the reaction forces. They look at this, especially you make the free body diagram, which we'll have coming up, and you say, well, I only see two forces, one up, one down. Those must be the reaction forces. But they're not. Reaction forces are always force of 1 on 2 is equal to minus the force of 2 on 1. And the force of gravity is not between my hand and this mass. It's between this mass and the earth. So the reaction force to the force of gravity has to be acting on the earth between the earth and this mass. All right. This list we saw before. I took off the fundamental forces, but otherwise it's the same as the slide we saw last class period. And so we're just going to go through and define these forces and look at how we solve some problems with some of them. So starting right off, I like the cartoon. It makes me laugh, and it's got physics in it. So, you see the guy going up for the dunk, his teammate, gravity, Vince, you forgot gravity. And just like Wile E. Coyote, suddenly he realizes, uh-oh, and falls straight down. So I put this here so I can illustrate gravity. When he's right here in the picture, he's in free fall. There's nothing pushing him or pulling on him except for one thing. And what's that one thing? Gravity that he forgot. Let's look at a common misconception right now. That common misconception is, well, how did he get here? I'm starting with reasonable questions to lead you to the misconception. How did he get here to begin with? He jumped. Was there a force involved when he jumped? Yes, there was a force involved when he jumped. Now, when he jumped, you start, okay, got to take your phone out so you don't drop that. So you start, you push on the ground. Now, normally, am I push on the ground? Yes. So how's it any different when I jump than when I'm not jumping? Why do you go up when you jump and not when you jump? Okay, I'm pushing harder. So I'm pushing on the ground harder. If I push on the ground harder, what does Newton's third law says is going to happen to me? Because the ground is then going to push harder on me because it's going to be equal magnitude, opposite direction. And so when I jump, the ground is actually what pushed me up. I pushed down the ground. The Newton's third law of reaction force pushed back, and that's what made me go up. And how long or when does the force of the ground pushing on me end? So as soon as I leave the ground, that force is gone. And of course, that kind of leap will never get you a dunk. In my life, I have dunked lots of volleyballs and a basketball exactly once. And I thought nobody saw me. The next day in class, a student said, "Hey, I saw you throw it down last night." I was so proud. Because let's just say that it was never an easy thing for me. So when you're in the air, as soon as your feet leave the ground, there is no longer a force from your jump pushing you. So many people, smart people, think that, well, because there was a force pushing when I jumped off the ground and I keep moving, there must still be a force pushing. But it's not. You're not touching it. So the only force there is gravity. He's in free fall. So if I take this and I do a free body diagram, what am I going to have for the free body diagram? I'm going to have a force of gravity. Now I have at the bottom what force of gravity is, but right now let's pretend we don't have the equation that's at the bottom of the screen. But we do know if something's in free fall, we know its acceleration. What's that? Okay, so it has an acceleration equal to, and I'm going to use vector signs just to make my life a little easier here with plus signs and minus signs. Use a vector sign, I'm good. So my acceleration is the g vector. The g vector is 9.80 meters per second squared and pointing down. Actually, I think on the test it's going to say to use 9.81. If the problem says use 9.81, go ahead and use it, right? Okay, so now we can use Newton's second law. We have our free body diagram, the simplest free body diagram that can exist if you actually have forces. And so I just apply Newton's second law. So I'm just going to say, the sum of the forces on my object is equal to the mass times the acceleration of my object. That's how you start Newton's second law. You write down the stinking equation. And then the left side where it says sum of the forces, I replace by putting all of the forces. In this case, there's 1. So that's just going to become the force of gravity, so the left side, is equal to mass times g vector on the right side. And that's where we get the relationship that the force of gravity is mg. Right? That's about as simple as you can have for deriving anything. And it's your simplest case of using Newton's second law. Colton has a question.
I know we tend to ignore it when we're doing equations, but does air resistance have a force?
Air resistance is indeed a force, and we tend to ignore it. But like we saw when I showed the trajectory of, like a baseball, it does have significant impacts. Let's say you're skydiving. If you're skydiving and you're in a spread eagle position, you have a terminal velocity that's somewhere around 55, 60 miles per hour. That means you speed up and your acceleration gets lower and lower until it gets to 0 when you get to that speed. Why? It's because when you're skydiving, so let's just use this picture of Vince when he was lower on the ground, you have the force of gravity that's mg, but then you also have an upward force that's the force of air resistance that has a value that's some constant. It's either multiplied by your speed or multiplied by your speed squared, depending on how fast you're going. So I'm going to go with speed squared. And that B number has to do with the air, your size, and your shape. So for instance, if you're spread eagle, that B is going to be a bigger number. If you're, like a javelin going down, that B is a much smaller number. And so you have one force that depends on speed and one that doesn't. You will speed up until the two forces are the same magnitude. Then your net force is 0. And according to Newton's second law, when your net force is 0, your acceleration must be 0. I'm looking for mouths moving to Southwestern. It's kind of hard when they know I don't hear them. All right. Of course, I had this in Wednesday's lecture, but I didn't get to it. In tribute to Wednesday's Apple extravaganza, where they announced the new iPhone 7. We've all seen pictures of or heard about Newton and his apple, something that very well probably didn't happen. It was something he used as an example to explain an idea. And so it's kind of important to understand what the idea of this is, just because everybody knows a few things about Newton. One of them is about Newton's apple. Shoot, there used to be a TV store or show, Newton's apple. And, well, we'll see in the next slide, the first iteration of what we might consider became this was the Apple Newton, because Apple Newton. So what's going on here? Did I explain to you guys before what the importance of this was? Because I have the astronomy class and I go through basic physics there too. No? Okay. His explanation involving the tree was talking about the force of gravity, the force that attracts one body to another. And his real revelation was thinking about, there's an apple up there in the tree and it's being contacted by the tree. And we all understand if I push on something, it's going to push back on me. Or if I pull on something, it's going to pull back. So no problem with there being force of the apple when it's on the tree. But once it broke free, unlike Aristotle's idea that it would just fall at a constant speed, they'd already determined it's going to speed up, it's going to accelerate. That came from Galileo. And he had just said, but acceleration means you have to have a net force. Something has to be pulling it down even when it's not touching anything. And that was a novel idea, that you could have force at a distance. And it makes sense, When we get to particle physics, we'll talk about this. I have this ball. If I want to put a force on Colton, I throw it. Then when he caught it, put a force on him, right? We had something that mediated the force. But I couldn't just go and put a force on Colton. So the idea of having a force act at distance, that was foreign to people in Newton's time. And he said, no, there must have been something, a force pulling down the apple even when it was touching nothing, just floating there in the air. And so he came up with the idea of gravity being a force at a distance. And that's what the whole Newton's apple thing is about, that you have a force acting when there's nothing touching. And so Newton came up with this equation for what we call universal gravitation that says the force between two objects is always attractive and is proportional to the two masses divided by the separation squared and then times a constant. Now, we're not going to actually have this introduced in the textbook for another couple chapters. So it's not something that right now you're going to have problems on. But since we're talking about gravity, it's good to have an idea of what gravity is instead of it's out there and sometime we'll explain it. In fact, if we're going to get that far, the understanding of gravity now is not the same as even Newton's universal law of gravitation. The understanding of gravity now, thanks to Albert Einstein, his theory of general relativity, is that gravity is actually the result of the warping of the space-time continuum caused by a mass. According to general relativity, a mass warps the space and times around it so that it makes it, things look like they're accelerating just because of the squished space-time. And so that's the best understanding we have about gravity. And now, of course, anyone with a mind to say, then why are we spending time learning this old, disproven theory of gravity? And the reason is, in every single situation you're ever going to face in life, this equation perfectly describes how gravity works. In fact, in virtually every situation, unless you become an astronaut, this equation here is going to describe how gravity works. The reason is, unless you become an astronaut, you're pretty much going to be standing on the surface of the Earth. Now, yes, you could go up to, the top of Long's Peak, or you could go down to, Badwater in Death Valley. But the difference in those elevations is really small compared to the radius of the Earth. So for all intents and purposes, you're always going to be at the radius of the Earth from the center of the Earth. And the mass of the Earth, of course, is going to stay the same. So that means everything inside of that parentheses is a constant. And so we just simplify and call that constant the acceleration of gravity, g. Now, if you become an astronaut, which would be so cool, you go up and you orbit around the Earth, the International Space Station. You're far enough away that the acceleration of gravity is like only 90 to 80% of what it is here on Earth. It's still a pretty big acceleration up there, but you feel weightless. Weightless means you feel like there's no gravity acting on you. How could that be? Well, you're in a. Where's the answer? No, Jonathan?
Isn't it because you're kept accelerating because you're changing direction by going in orbit?
Okay. You're accelerating, going in a circle, and that acceleration toward the center is what we call centripetal, toward the center acceleration. And you're inside the International Space Station that's doing the same thing. So it's accelerating with you. It's like if you were to get into an elevator car, and then the elevator car has all the cables snapped and the brakes aren't present. Right, there's brakes in an elevator, so if the cables snap, you stop anyway. But if that thing were just to fall and you're inside, you'd feel like you're weightless. You could float until you hit the ground. Then it would stop, and then you would stop. Hence, when I was in graduate school, now you guys probably have a feeling that physics people are nerds. The people that were a year behind me, they were the nerds. They thought it was funny as all get out. We had, 7 stories in our physics building there at Washington State, Goku's. And the classrooms were on the bottom floor in the basement. And so we all would take the elevator down to the classrooms. And so when they were coming to class, they would lie on the floor of the elevator. And when the elevator stopped, they would all bang their hands on the floor so it sounded like there are people crashing down. And then the elevator doors open, everybody sees all these students lying on the ground. Yeah. They thought it was hilarious. Because they were physicists, they knew about, free fall and all this stuff. And they were super nerdy. Those in my class were not nearly so nerdy. Okay, you can answer this starting now. What was revolutionary about Newton's apple, which is not to be confused with that apple Newton? Or a fig Newton, for that matter. One can hope. It's a good thing that and that are wired, so we don't have to worry. Okay, I give you another 10 seconds. Alrighty. So we have 1, 23, 20, and 5. So what was revolutionary? I'm not going to have people discuss because this is really just a, yes, no, I understood or didn't understand when you said it. It showed that forces could act at a distance. That's what was revolutionary about the whole Newton's apple thing, that forces didn't require contact. Little historical note, just in case you're wondering about the whole iPhone thing, Apple did not invent the smartphone. Cyan Organizer was the first public digital assistant, PDA. The Apple Newton was the first thing to actually be called a public personal digital assistant. And then the first personal digital assistant that has a phone was released in 1994. So you'd have to consider the IBM Simon to be the first actual smartphone. Now we call PDAs with full cell phone, like your Samsung, S7 Note that's going to burn a hole in your house. We call them smartphones rather than PDAs. Okay. First force we talked about here specifically was the gravitational force. Now the normal force. This picture on the right, that's the definition from Wikipedia and a picture from Wikipedia, just to make sure we know what the word normal means. When I say normal, that's a direction. It's the three-dimensional equivalent of perpendicular. Right. Perpendicular is at 9 degrees. Normal is at 9 degrees to any line you could draw in a surface. So I have a tabletop. Any line I draw is going to be horizontal on the tabletop. And so normal has to be perpendicular to all of those lines. The only two directions that are normal to the surface are straight up or straight down, right? If it's a horizontal tabletop. And the normal is the direction coming out. So the normal to the tabletop is straight up. What about the normal to, yeah, they can see that. What about the normal to this side right here? Straight that direction, because it's got to be coming straight out of the surface. So when we talk about the normal force, it's the force in the normal direction. What's the purpose of a normal force? It's to keep things from going through a surface. You have a solid surface, things don't go through, and that's the normal force that keeps them from going through. Just want to play fun. That's fine. So the normal force keeps things from going through. Well, what's going to make it so I can't fall through the floor? What force makes it so I don't fall through the floor? Okay, normal force is the force that keeps you from falling through the floor, but what makes that normal force? Rachel? Okay, it's solid. What do you say, Jordan?
The bonds between the atoms.
It's the bonds between the atoms. The atoms are bonded together and don't easily come apart. And since they don't easily come apart, when I push down on it, they get pulled a little bit, but then they just flex a little bit and push up and stay together. And so it's actually electromagnetic force that is keeping me from falling through the floor. So electromagnetic force is what causes the normal force. Now, we're not even going to talk about electromagnetic force until second semester. So at no time in first semester on a test are you going to answer, oh, that's electromagnetic force. You'll just say, that's normal force. That's electromagnetic force that is the fundamental force causing the normal force. So here we have two pictures. The top one, two children pushing a wagon with the third child inside. Free body diagram is always the first way you attack a problem. Assumedly, they're going to have, the acceleration is this, and the girls are pushing this hard, what's the force of friction, or something like that. Right? You have to have actually what they're asking for before you know how to actually solve the problem. But you're going to almost always say, oh, I need to work with the forces, I need to add them up. So if I need to add them up, I need a free body diagram. Right? So when we get to our concepts, we're starting to put more pieces in. Not just, well, it's moving. I'm just describing how it's moving, kinematic equations. Right now it's getting more complicated. So in the upper picture, we have two girls pushing. So we have force 1 and force 2. That are the two girls pushing. We have the force of friction down here. That's, in this case, rolling friction is the term we give to the friction when something's rolling. And then we have the force of gravity, which is labeled W. Let me zoom in a little. And the force keeping the wagon from sinking into the ground, the normal force, which they labeled N. So free body diagram is made simply by showing those forces all acting on one point. Like I said, I would be more than happy if you just left it like this, right? As long as you have it so it's laid out and I can see what the forces are acting. Another thing that is confusing to some people, other people don't even think about it. I'm one of the ones that don't think about it. How do you show your arrows? If you look at these, this arrow here is supposed to be from where her hand is applying the force to the right. This one here from where her hand is applying the force to the right. This one here from the wagon downward. This one here from somewhere in the earth upward. This one here from somewhere in front to the left. There is not a uniform, the arrows either start at the object or end, it doesn't say they all start at the object or they all end at the object. It just has to show them all. So don't get concerned if you show the weight below going down or above going down, as long as you have it there. Some people get bent out of shape and they say, no, it needs to be something like, like this here showing the forces all acting on one point going out in whichever direction they go. I don't care. I just care that you show them correctly. So that's the picture with the two people pushing. With one person pushing, it's only different in that you have the force of an adult. Notice the acceleration is shown. Make sure you don't confuse the acceleration with a force. Make sure there's some way to tell the difference. Because if you start doing your problem and you get confused, well, that is problematic. Didn't mean that to sound stupid, but I did. Another common misconception students have, the reason it's in the textbook, is when there is a normal force and when there is not. Normal force, by its very nature, is a contact force. So in the first picture where the bow wow chow is not sitting on the table is not going to apply normal force because normal force is a contact force. Oftentimes people, they start getting comfortable with normal force and then they just try to put normal force in everything. But in the upper picture, there's the force of the hands pushing up and the force of gravity pushing down, and that's it. The second picture sitting on the table, then you have the normal force. Yes, sir.
So it would be the normal force from the bow wow chow going through your hand?
Normally, we don't call it a normal force if it's something other than a fixed object. So your hand, we'd say that's you. When you get down to it, once again, what keeps the bow wow chow from falling through your hands? Well, it's the same electromagnetic force, but we tend to call it a different name. Now, if we were to look at this situation right here, what's the acceleration?
Point.
Going to go with 0, right? Because it's sitting on the tabletop. Sitting on the tabletop, its velocity is constant at 0. Now, it could be moving at a constant velocity and also have 0 acceleration. That's another misconception people have. But it has acceleration of 0. So if I use Newton's second law, some of the forces, I need a direction. This doesn't show direction, so I am going to draw it. On your problems, if it doesn't show directions, make sure you define them. So now I'm going to do some of the forces in the direction I defined as y. I defined y as up. So now I look at the picture and I say, what forces do I have in the vertical direction on that bow wow chow? Say louder, Gila. Okay, I have the normal and the gravity. And so now I'm going to rewrite force normal and force gravity because I like to have F for all my forces. So taking Newton's second law, and I should have put some of the forces in the y direction is equal to mass times acceleration in the y direction, right? Just like independence of motion we had with trajectories. So then for my picture, of the two forces that Gila named, the force normal and the force of gravity, are any of them, we all know the answer, are any of them in the positive y direction? Yes. And then, of course, the follow-up, the important one, which one is in the positive y direction? The force normal. And so when I write that in the substitution for some of the forces, it has a positive sign because it's in the positive y direction. So what about the force of gravity that's in the negative y direction? Does it have a plus sign or a minus sign? Minus sign because it's in the minus y direction. So I have force normal minus the force of gravity is equal to mass times, and what was the acceleration? Why, it was 0. And so then I can solve to find force normal. Force normal is equal to the force of gravity in this case. Shocking. Well, let's say that I modify it. Let's say that I laid hands on this and I pushed down with the force hand. How would that have changed the work that I just did?
Force normal would equal force gravity plus force hands pushing down.
Okay, you got the answer right. How'd you get there?
Well, the net force is going to be all of the forces acting on it. So you'd have to include that now.
Right.
In the equation.
Okay, stop that. So I have minus the force of the hand there. And so adding force of gravity and force of the hand to both sides. I get to the answer that Colton gave us. That the force normal is now bigger than the force of gravity because there was additional downward force that the table still had to keep opposing. Oh man, I only have 1 minute left. Life is bad because I have about half my slides left. Here is a pretty picture of a snow skier. Probably many of us love to snow ski, although I found as I got older, I got a lot colder, so not as much anymore. We will analyze the forces on this gentleman, or this, yeah, it's a gentleman too. The first picture I have is a lady, on Wednesday.